Okay, so what I want to talk about today is, well, stuff that can be found on the archive, but basically what I want to talk about is electronic band theory, but it can obviously be applied to phonons and other things, but and really I want to talk about electronic band theory without Hamiltonians. So when we have a lattice and we have a periodic arrangement of atoms, what physicists like to do is immediately draw a Brillouin zone, like everybody does, and plot the band structures or the energy bands versus some momentum in this Brillouin zone. So that's what we usually do. And the reason why we do that is because the physics in momentum space is diagonal. So the Hamiltonian for periodic systems in momentum space is already diagonalized. And then we know immediately, that's why we can plot the energies. These are just the quantum numbers of the diagonalized Hamiltonian versus momentum. And we plot the energies versus some parameter, which is the momentum. Now, the problem with this is that this type of approach kind of obfuscates the physics and the chemistry of the problem, because what we really started from were real lattices with orbitals sitting in real space at some lattice size. Now, of course, the Heisenberg principle tells us that momentum and real space are not measurable at the same time. So plotting something in momentum means plotting something extended in real space, and vice versa. So basically, there's this kind of disconnect between chemistry, which has orbitals at certain lattice points, and physics, which basically likes to describe things in momentum space, likes to describe Hamiltonians. And what I'm trying to, what I basically want to point out is that we don't need to think about Hamiltonians, we don't need to think about energies, and what we should be thinking about is really what does the chemistry tell us about the physics, but what does the chemistry tell us about the universal properties of the physics? So since energies can obviously not be universal, let's forget about the energies. So let's forget about this type of thing. But there are some properties that can be universal. For example, there can be, in systems with a lot of bands, the bands can look either like this, or they can look like this. They can be connected in the Brillouin zone, etc., especially if I have a more complicated Brillouin zone. So for example, there is a question of how many bands are connected here, and we can ask whether that question is answerable by energetics or by other means. And the answer is that it's not answerable by energetics. The shape of these bands, the way they look, is answerable by energetics, but the way they connect in the Brillouin zone is a universal property that we can actually derive straight from the real space chemistry, and this I'll show you. Moreover, this would be kind of a, not to just do this type of theory for just finding out connectivities in the Brillouin zone would be kind of an overkill. But what I'll show you, and hopefully when I get to the punchline, is that if you just take into account an approach that looks at both real space and momentum space, you can actually classify all topological insulators and semimetals that exist in nature. And moreover, classifications are not really predictive, but what this theory will allow you, it will allow you to say where in real space do they come from. So in other words, it will allow you to say what orbitals do I need at what position in what lattice, in what symmetry group, to realize the topological phase X. Okay, so that's obviously a very fundamental and important thing, because unlike a classification which tells you that things can exist, this will tell you how things can exist, or what is needed to build them. And because of that, of course, you'll be able to make predictions of real systems in which things that you proved should exist will exist. Okay, so let me just give you some numbers. So in periodic systems, or in lattices, there's 200 in 3 dimensions. There's 230 space symmetry groups. And this theory will take into account all of them. Most of them are non-symmorphic, although the example I will do is symmorphic, just for. So non-symmorphic means something that looks like this, okay? Where if I have a unit cell, you can see that I need to make a mirror plus half a lattice translation to get back to itself. So these are non-symmorphic. I won't be talking about them very much, but most of these space groups are actually non-symmorphic, and this in 3 dimensions. In 2 dimensions, there's 17 so-called wallpaper groups, and they're called wallpaper because of obvious reasons. And they're the groups of symmetry, space symmetries of 2-dimensional systems. Now, our example will be one of these groups, and will be group number 17, the most symmetric one, which is the hexagonal, basically the hexagonal lattice. And we'll do the full theory, but then we'll run through these examples. Okay, so what are the ingredients of the theory, and what are the outcomes? The ingredients are the symmetry group, the orbitals sitting, the orbitals of the atoms that you're putting in your lattice. That's how materials get built. I have some orbitals in a symmetry group. And number 3, the position of these orbitals. So orbitals are just the valence orbitals of some atom, which you know them by knowing the atom, and position of atoms on lattices. So given this, we can ask, what can we get without a Hamiltonian? And the answer is, again, quite a lot. We can get a predictive power for all predictive and descriptive the theory of all, I should put crystalline also, TIs and semimetals. Okay, so this the way we get from here to here will have 2 parts. Part number 1 is describing the symmetry groups and looking at what's important out of the symmetry group. So let's start with that. So a lattice is obviously a periodic arrangement of atoms, and this periodic arrangement of atoms, I'm going to be working in 2 dimensions for simplicity. This periodic arrangement of atoms has 2 lattice unit vectors, and I'm going to write them for the hexagonal lattice, which will be the zeitgeist of our examples. By the way, interrupt me, please. Otherwise, okay. These are the 2 unit vectors of the hexagonal lattice, and we can write them down. Their length 1, as you can see. Okay. So first is the lattice, and its symmetry group, and the symmetry group of this lattice, which will actually, we're going to use this quite a lot, so I'm just going to write it down here and keep it here. sorry for the doubling. So if somebody can tell me the symmetry group of this lattice while I redraw things that should have been drawn the first time, that would be, well, that would be nice. So what is the symmetry group of this lattice? Just the lattice. I haven't put orbitals on it. So does it have 6-fold rotation? So does it or does it not? Sorry? So it doesn't have 6-fold rotation? So it has 6-fold, but 6-fold is, so it has 6-fold rotation, so it has C6. Which implies that it has C3 and C2. So we're just writing the generators of the group, very good. This is this squared, this is this to the cube. What else does it have? Thank you. And it has actually 2 mirrors, but as a generator you just need one of them. And I'm going to write the mirror as in this type of basis. Do we have more chalk? Yeah, we do have more chalk. Brilliant. Where this means that this axis that I drew, that I pointed here, gets flipped on the mirror. So this is E1, this is E2, this is 1, 1 bar, this is E1 minus E2, E1 minus E2. This is, when I write 1, 1 bar, is in E1, E2 coordinates. Okay? So this means E1 minus E2, which is just Y, gets flipped. So this is this mirror plane, if I was to look in this direction, or this mirror. So I flip around this mirror axis, then that makes this go into minus itself. Okay? So let's define these symmetries. So M11 bar takes E1 and E2 and sends them into E2 and E1. Is that clear? M11 bar is the mirror symmetry. Mx is the symmetry that takes x to minus x. 1, 1 bar takes 1, 1 bar, which is E1 minus E2, which is y into minus y. So it's this plane. And this plane takes E1 into E2 and E2 into E1. Is that clear? Okay. C3 takes E1 and E2. What does it take E1 into? C3 takes E1 into? Thank you. And it takes E2 into E1 minus E2. Yeah? Make sense? Flips this guy here, minus E2, takes E2 here. These are the symmetries. And, of course, C2. So, you know, I could just say C6, but we're going to need these for later, so we're just going to put them like this. C6 takes E1, E2. C2 takes E1, E2. C2 is, of course, 180-degree rotation. Where does it take them? So, like, it's you know, we're not going to pass page 10 if we and like this is going to be interactive, because you know. Sorry. Thank you. Very good. Huh? So C2 has to take, you know, flip vector. So it takes E1 to minus E1. It's a 180-degree rotation. No. It's a 180-degree rotation. E2 becomes minus E2. It's a 180-degree rotation, right? So just take this vector. Forget about E1 and E2. Just one dimension. Take this vector, flip it by 180 degrees. What does it do? It goes into, okay, very good. Thanks. Okay, so these are the symmetries of this lattice. Now, what we want to do is add atoms on this lattice. And first of all, I'm not going to tell you what atoms we add. Just assume we add any atom. We're going to particularize. We will need to give more information. So by the way, the information that I gave here, symmetry group orbitals, etc., is the information that you can just get from any database of materials, because you know where the atoms sit because of X-ray diffraction, and you know the symmetry group of the system, and you know the valence orbitals because you've got the periodic table at hand. So it's a minimal set of information, but it's very powerful. Okay, so now I'm going to tell you that the atoms sit at position Q. Let's say atoms sit at position Q. In the unit cell. So it's pretty obvious that because I have these translation vectors, I only need to talk about the unit cell, because everything else repeats. And atoms sit at position Q in the unit cell. And this Q is called a Wyckoff position, or part of a Wyckoff position. Which, and in its most general form, just means nothing because the atoms can sit anywhere on the lattice. We'll find out that some Wyckoff positions are better than others, and we'll find that out soon. So now, if there exists an atom at Q, there will exist an atom at all, there exist atoms at all G times Q, where G belongs to the space symmetry group of the lattice, which in this case is P6 something. Anybody knows what the number is? P6, or it's number 17, but anyways, it's P something. It's the symmetry group is this one, is given by these, well, these elements plus translations by E1 and E2, plus these elements, and it's pretty clear that if I have a symmetry group and I have an atom at Q, I'll have atoms at other positions which are related to Q by the action of the symmetry group. Okay, so we're going to write the space symmetry group G of the lattice as a rotation element plus a translation. This is the notation, well, this is notation that people adopt for symmetry groups. And these rotation elements just belong to either these, and this translation is any linear combination with integer coefficients of E1 and E2. Yes? So Wyckoff position is any position in the lattice. Just, it's a name. So far, it's useless. It will become very useful very soon.
What's that argument for the first symmetry?
Which one?
The one, yeah.
This is M11 bar. So, as I said, M11 bar takes 11 bar, which is 1 means E1, 1 bar means minus. This other one is E2. So this is Y, and flips it into minus 1 bar, which is minus Y. Okay? So in effect, so it does this. So if you look, it's just the mirror around 1 bar is this direction. You index mirrors by the plane that by the axis they're perpendicular. So you take this guy and you flip. You just take it and you flip it like this. So this takes E1 into E2 and E2 into E1. Okay? Good. Okay, so the symmetry group will be, the space symmetry group will be indexed by some R, some element of these rotations and mirrors and translation. Okay? And if there's an atom at Q, there's an atom at G times Q, where G is any element of the space group, including translations, etc. But, so we're going to call the orbit of Q, these are just group theory, orbit of Q, are all the sites G, Q, where G belongs to the space group. So in other words, if I have an atom here, I'm going to get one here, one here, one here, one here, one here, then by translation one here, everywhere. Okay? This is just, so far I'm telling you trivialities for 20 minutes. Okay? So, okay, now the point is that we can now define what's called a stabilizer group. Which, of course, is the group destabilizing the position Q. So if I have an atom at Q, I can find a group that leaves that point invariant. So the stabilizer group of Q, which is called GQ, is made out of all elements G such that it leaves the site Q invariant. Okay? Or the position Q on the lattice invariant. What is the site symmetry group of some nonsense, any position here? Say I would put an atom somehow here, not on the corners, but here. What's the site symmetry group of that? What leaves that invariant? No, it's not on this line. Just any point, not on a special symmetry point. Identity. Okay, so the simplest site symmetry group is the trivial group, is the identity. It does nothing to it. If I have a point which is not special in the unit cell, the site symmetry group is identity. If I have a point that's special in the unit cell, it'll be larger, and those are important. Yes. So the stabilizer group is what? The stabilizer group is the group that leaves the point invariant, but invariant modulus translation. So yes, so very good. So very good. So I will choose it. Thank you for this question. I will choose it so I can always back up translations into this group, so that it leaves it invariant, not invariant modular translations. So this really leaves it invariant. I didn't mod out translations. So this is really leaves it invariant. And the reason why I want to do this, which is, thank you for your question, is because this is then isomorphic to a point group. So space groups, as I showed you, involve translations. And it's not only that they involve translations. If I have non-symmorphic space groups, they involve translations by partial unit cells. Point groups just leave point invariants. By definition, the stabilizer group is a point group. And that's very good, because there's only 32 point groups in nature, and we can classify all of them. Well, we classified all the 230 space groups, but it doesn't, well, based on this theory, but the point is, you want to get the most information you can, and basically, this is, you just make the stabilizer group be a point group, okay? So it leaves this point invariant, and now I'm going to give some examples. So obviously, this means nothing if I pick just a random point on the lattice, because this stabilizer group is identity, but if my Wick position, part of the Wick position, so Q belongs to a Wick position, okay? And the orbit of Q, which are all the elements that are, all the positions that are obtained by acting with a group on Q, this is called the Wick position. So Wick position is a set of positions. And Q belongs to a Wick position, okay? So I say, here's my point, act with all the elements of the group in the unit cell. So in the unit cell. So without the translations. And then I get the full Wick position. Okay, let's do some examples. So Q, I pick Q is E1 minus E2 over 2. What's this point? Where does this sit on this lattice? Where's this Wick opposition? Let's call it, for anticipating things, 3C. Okay? We just index it by 3C for reasons that are. Where does this sit? Come on. Sits here. Right? It's Y. This is my origin. E1 minus E2 is just Y, so it's Y, well, yeah, so it sits here. Y over 2. Okay? What is the side symmetry group of this guy? GQ3C is what? What is it? What's the side symmetry group of this guy? Come on. Please. So the side symmetry group of this guy is obviously C2 is part of it. Why? Because C2 changes this guy into this guy. Okay? But this guy is related to this guy by a lattice translation. So I can build an element called C2 with E1 minus E2. So C2 rotation plus a translation. C2 takes this from here to here. Then I translate it back by E1 minus E2. This leaves this point invariant. Yes? So this group element, C2 plus a translation, belongs to the side symmetry group of this guy. Yes?
Can you remind what the side symmetry group was?
So the side symmetry group is the group, sorry, the stabilizer, very good, thank you. The side symmetry group is the same thing as the stabilizer group. Very good. I apologize. They're used interchangeably, and, you know, for dyslexic reasons, I guess it's not really dyslexia, it's just for some reasons. So side symmetry group and stabilizer group are the same thing. Thank you. Okay, so the stabilizer group or side symmetry group contains the C2 element. What other element does it contain? It contains mirror 1, 1, okay? Because mirror 1, 1, not 1, 1 bar, 1, 1 mirror is E1 plus E2 is X mirror. So it's the mirror that sends X to minus X. And you can see that it's invariant under this. Of course, in the generators of this space group, I didn't add M11 by itself because M11 can be obtained by rotation of M11 bar. So I just added the generators. But M11 does belong, you see, this is the symmetry of the lattice. So it does belong to the symmetry space group of the lattice. So M11 is part of this side symmetry group of this guy. And I claim that this is isomorphic to C2V. V just says C2 plus a mirror. So even though it's got this translation part, you really shouldn't look at it as, it shouldn't be like, oh, wow, it's got a translation part, so it's not, you know, it's something weird. It's not. It's just that my C2 element is not just a rotation, it's a rotation plus a translation. But this is isomorphic to C2V, which is the symmetry group of C2 and mirror. You know, and the isomorphism is clear. This goes into this, and this goes into this. Yes? This. Sorry? This mirror would leave this invariant because it's sitting on the mirror plane. This guy sends this guy into this guy, and this guy is related to this guy. So yeah, so, but that's just this mirror times this mirror, times this. M11 bar also, M11 bar, you see, M11 bar plus a lattice translation is also in the mirror, in the side symmetry group of this guy, but that can be composed just by this times this. These are just the generators. Very good. Is that clear to everyone? Okay. Okay, so the other stabilizer side symmetry group that we will use, which is the most important one, because that's where the atoms sit, is the side symmetry group of the position of this guy, of this position. So this position is the position Q2B I just index it by these numbers, which will come out later, which is E1 plus E2 over 3. Okay? That's this guy. Can somebody tell me what the side symmetry group or the stabilizer group of this position is? What do they think it is? Certainly M1, very good. So it's GCQ2B. Certainly has M11 bar. What else does it have? So you can see that if I make C2, if I put it here, C2 does it here. This is not a unit cell translation. It's a fraction of a unit cell translation. So C2 is not in the symmetry group. Very good. But what is it? So you can just prove that this is not a unit cell translation. It's a fraction of it. So what is it? C3 times translation. And I can give you the translation, and you can check it. I checked it for you on the notes, which will not be LaTeX ever, at least by me. So C3 times plus a translation by E2. Okay? C3 plus translation by E2 leaves this guy invariant because C3 moves Q2B from here to here, but this is related to this by this translation. Okay? So this is the side symmetry group, and this is isomorphic to C3V. This V just tells you that I have a mirror plane which contains the C3 axis. Okay? And the isomorphism is again clear. This goes into mirror, this goes into C3. Don't look that it's got a translation. We can find the translation later. Okay? I mean, not find the translation later. You can prove that with the translation. We just found the translation. You can prove that with the translation, it is a side symmetry group, and it's a very simple application of these. The other position, which we call Q1A, is the center of the lattice, Wick position. The things that I'm giving you now are special Wick positions, obviously. That's why we're talking about them. And this is invariant under what size symmetry group? The whole group, whole point group. Okay? Now, there's another Wick position that I'm going to be talking about. And this is the Wick position connecting these two sides. So I draw a line here, and I put a Wick position here, call it QX. And QX is the Wick position X E1 plus E2, where X varies from 0 to 1/3. Why is this important? Well, notice that I put not closed interval. All the side symmetry group of all these Wick positions here is the same. What is it? What's the side symmetry group of this Wick position? M what? Exactly. And it's the same for all x's. Okay? And notice that it interpolates between two other Wick positions, 1A and 2B. Obviously, it's the high symmetry line in the lattice. Okay? All right. Now let's find the orbits. So now we find the orbits of all these Wick positions. The reason why we're doing this is to basically characterize the positions where we can put atoms and see if some of them are special. And the answer is some of them are special. So that's why we're going through this painful exercise. So what are the orbits? Well, they're all the distinct points on the lattice that the elements of the space group send the Wick position into modulo translations. Okay? In the unit cell. So in the unit cell means modulo translations. So for Q3C, so my Q3C is this guy. What are the orbits? Well, if I apply any of this group, this stays invariant. So doesn't do anything. But if I apply elements which don't sit in stabilizer in the site symmetry group, but are part of the full space group, like C3, this guy takes this guy here, right? This is not identical to this by a lattice translation. So this is also a new Wick opposition, which we call it Q. Well, it's part of the same Wick opposition, but it's a new position in this Wick opposition is this orbit of Q, okay? And, you know, I can translate it by a unit cell translation here. So I apply C3C, I translate it here, okay? And I apply C3 twice, I go here, which is identical to this one, by a unit cell translation. So I have, and that's it. So notice that I have, in this Wick opposition, I have 3 sites, and that's where this 3 comes from. This is called the multiplicity of the Wick opposition. Multiplicity 3. And notice that the way you obtain it is very reminiscent of the orbits in group theory. You take an element, C3, which was not part of the site symmetry group, and you act on the vector of the site symmetry, or the vector that the site symmetry group leaves invariant. You act with it on it to form all the possible vectors. Yes.
Why do you make the translation?
Because I said in the unit cell. So if you want to choose, you know, so I'm allowed to make translations. Basically, the Wick opposition is defined as the orbit of Q in the unit cell. So you can put it, you know, I can define a weird unit cell where I take these 3, but I can put it like, I can just take these 3 to be anything that's invariant by a lattice translation can be brought into the same unit cell.
I mean, why are those the 3 Wick oppositions related to the? Why are those the orbits?
So if it makes, so this is T3 plus a translation, T3 square plus translation. If it's easier to swallow, put C6 to the -1 QC3 and C6 Q3C. C6 is also not part of C2V. Okay? You can choose there's a theorem in group theory called the Orb Stabilizer Theorem, which tells you can pick a set of elements. There's no unique, there's a unique coset decomposition, by the way, but the way you get those cosets is easy. You can pick any coset representatives. So those guys are just these. Okay? Do you agree that these guys are just those? Okay.
If you just do a C3 rotation, then that couldn't be the Wick opposition.
Well, this point is identical to this one by translation, so I can't count it twice. So you can count this one. I can make a theory where I count this one and this one, or where I count this one and this one. That doesn't matter. It's the same. But you can't count it twice because you're looking at things in the unit cell. So if this guy is not the same as this guy by a translation, or as this guy. So that's why I have to count them. But you can't count things related by, yes?
Q3C, Q3V are like Wick points, but QX is the Wick length.
Sorry, which one?
Q3C and Q2V are like Wick points, but QX is like Wick length.
Qx is a Wick point defined by x, but it's a Wick. You have the Wick position is all that line of points. In that case, so Wick position is the is the line of points because I'm in the unit cell. So here is just it's this whole line of points. Sorry. Well, okay. So you can. Okay, fine. So let's take the Wick position to just be 1 point given by 1x. The point is, as I move this point, it's going to be basically the same symmetry group. So I don't have to change my analysis based on x. But if you want to define the Wick position, fine. We can define it just by basically putting, just by particularizing to 1x. But the point is the whole physics is going to be the same for the whole line. Very good, thank you. Okay, the Q2B stabilizer group is what? The Q2B stabilizer group is C3V. So I'm building the orbits. One orbit is Q2B, and the other orbit is C2 times Q2B, okay? Which is this guy. Okay? So this now has two elements. So it's multiplicity 2. Any other elements of the space group will give you translations plus these. Okay? These are the only two independent ones. This is not related to this by a translation, so I have to count it. Any other elements that I act are related by translations. Okay? And okay. Okay, and basically I would like, well, I mean, I proved it here, but basically there's a very easy way of obtaining, if I know the side symmetry group of Q2B, obtaining the side symmetry group of this guy, which is this guy, and that's just group conjugation. So basically, what you say is that if the side symmetry group of this guy is C2V, C3V, the side symmetry group of this guy is C2 to the minus 1, C3V, C2, or rather this one. So this is just element conjugation by this one. This is also isomorphic to C3V. So in other words, the side symmetry groups of any of the points in one Wick position are the same. So that's obvious, right? This is C3. This is also C3. It's just a different C3. It's not a different C3. It's got different generators, but it's the same group. Yeah? Does that make sense? Okay, good. Okay. So, so now basically what we can do is talk about the coset decomposition of the space group. And that basically means that the space group, the full space group, can decompose into orbits. Yes? You can write down the, I mean, these are implemented by computer. There's the coset decomposition. Yeah, as a matter of principle, you just take the side symmetry group, take all the elements of the space group that don't live in that side symmetry group, and so I'm doing it right now. So the coset decomposition, so the coset decomposition of G is a union of G alpha these are two translations. So let me explain this formula. So N is the Wick of multiplicity. So this formula says the fact, yes?
What do you mean by orbit now when you're saying I take this orbit then?
Right. So what I mean by orbit is I have a side symmetry group. It's invariant under some. I have a Wick position, like a position in lattice. It's invariant under some side symmetry group. Okay. Now what you do is you take all the elements of the space group that don't belong to the side symmetry group, and those what they actually do is they map different Wick positions into each other. So the side symmetry group leaves this invariant, so it can't do very much. But elements that don't live in this side symmetry group map this Wick position to others. So this guy, so for example, C3V is the Wick opposition. So C2 does not belong to C3V. So C2 takes this one and this one. That's creating orbits. So basically, when you create orbits, you just take elements of the group that don't belong, elements of the full space group that don't belong to the subgroup, to the stabilizer group, and you act on the elements of the stabilizer group. And there's a point, it's called an Orb Stabilizer Theorem in group theory, that basically says that given a subgroup, and this is what Professor Atlan was saying, that given GQ, given a subgroup of this full space group, I can form a coset decomposition of this space group into cosets of GQ. So what I take is G alpha, not belonging to GQ, but belonging to G, and I can rebuild the whole symmetry group G by just acting with G alphas, elements of G that don't belong to GQ, on GQ. And of course, since I have translations, I added also translations. These are just, think of these as just group elements. Right? Since this was defined within the unit cell, to build a full space group, I need to basically first rotate within the same unit cell and then add translations. Is that clear? That's called the Orb Stabilizer Theorem. And you can clearly see it here because if I have, you know, C3V as this, and now I have C2 times C3V, this generates the whole C6V. Okay? It's isomorphic to this. So this is the side symmetry group of this Wick opposition. This is the side symmetry group times the element G2. For this Wick opposition, this N is 2. I have two sites in this Wick opposition. And this is the full group C6. If I had translations, this is the full space group. Okay? So this can happen given any Wick opposition. So for example, if I pick this Wick opposition here, this symmetry group, the side symmetry group of this Wick opposition is C2V. But then the orbits, or these elements that don't belong, don't belong to the side symmetry group of this Wick opposition, so don't belong to C2V. There's C3V, and they map here to here. And then C6 is again C2V and C3 times C2V. Okay? All right. 7, 8. Okay, so now we're going to define what's called the maximal Wick opposition. So some Wick oppositions are better than others. And the maximal Wick opposition is the following. The maximal Wick opposition is a position that's not non-maximal, and a position that's a position whose symmetry group, so this is the position whose symmetry group is a maximal subgroup of the space group, whose side symmetry group is a maximal subgroup of the space group. So in other words, there's no other group between the Wick opposition stabilizer group and the space group. Okay, so which ones of these do you think is a maximal Wick opposition? The center of the unit cell is certainly a maximal Wick opposition, because that's really the full, there's really C6V, so there's nothing between C6V and C6V. Which other ones are? So very good. Which other ones are? Is this a maximal Wick opposition?
No.
Why? So it is. It is a maximal, but so the reason for it is that this symmetry group of this Wick opposition is C3V. Okay? Between C3V and C6V, there's no other group. I cannot write down this. Okay? Does that make sense? There's no other group in between C3V and C6V. So this is a maximal subgroup. So if I have another group, I would have the C3V is included in another group, which is included, not equal, to C6V, which is the site symmetry, the full, which is the, times translation, the full space group. So this is not possible, okay? Because, why? Well, because the only element that's missing from here to get this full group is C2. But once I add C2, I get to the full group. So there's no other group between them. So this is a maximal Wick opposition. Is this a maximal Wick opposition? Because the C2V, the only element that's missing is C3. But once I add C3, I don't find another group here. I find a full group. Okay? Okay, so maximal Wick oppositions are, in this lattice, Q1, Q2, Q1, 1A, multiplicity 1A, 2B, multiplicity 2. This B doesn't, it just indexes the fact that they're different. Q1A, Q2B, Q3C. Is QX a maximal Wick opposition? Why? Very good, so it's not. But why? What's the site symmetry group of QX? So what's the site symmetry group of QX? Huh? Mirror 1, 1 bar. But mirror 1, 1 bar is included in C2V. It's also included in C3V. This V just means mirror, which are included in the full space group C6V times translations. Okay? So there is another group in between the site symmetry group of this X and the full group. And that's obvious because this X interpolates between two maximal Wick oppositions. Okay? So at least the site symmetry group of this Wick opposition and the site symmetry group of this Wick opposition, the stabilizer groups, have to include the site symmetry group of this X Wick opposition. And this is just what this is saying. Yeah? Okay. Yes?
Remember why the C2V was not a maximal Wick opposition?
C2V was.
Why was not?
C2V, the site, this corresponding to site symmetry group C2V, which is this guy, is a maximal Wick opposition.
Oh, yeah, sorry. So
the X is not.
I meant the opposite. Why is it? Because
Why isn't?
in between it's C2V, but then you have the entire.
No. So this guy is a maximal Wick opposition. This guy is a maximal Wick opposition. In between, and in between is characterized not with square brackets here. So it doesn't contain the ends, right? In between is characterized with, so it doesn't contain 0 and 1/3. So it's just very little bit off here and very little bit off here. Any of these points. The site symmetry group of this is mirror 1, 1 bar. But mirror 1, 1 bar is included in C2V. V just means mirror. Is included in C3V, which also means mirror. But these are subgroups of the C6V, which is the symmetry group of the lattice. So there is a group in between the site symmetry group of the X position and the full symmetry group of the lattice. So this is not maximal. It's not the highest. Right? These guys are maximal. But I made the point that you can still think of this guy, you can still understand that this is not maximal just by noticing that it can kind of interpolates between these two. So this guy, because it interpolates between these two, has to be contained as a subgroup of this guy and of this guy, which is just this. Hence it cannot be. Does that make sense? Okay, thank you. Okay, so now I'm going to finish with the first part. We found everything that can be found about lattices, and you can classify this for all the 230 space groups, all the Wick oppositions. In 3D, it becomes a mess. It's a bit of a nightmare. But there is a point in doing this, and the point is that we now want to add orbitals. So now we're going to go to the chemistry and add orbitals. add orbitals to lattice, and ask, how do we form bands? Okay? Well, the moral of the story is that the universal properties of bands will depend only on the properties of representations of the groups of the maximal Wick positions. So that's why we did the maximal Wick positions, because only those are important when you're looking at adding orbitals. Even though the orbital might not sit on a maximal Wick position, it can sit somewhere else, all that is important for the properties of the bands is what the representations are at maximal Wick positions. Okay? So the point is, when I add orbitals on the lattice, there's all kinds of chemistry effects. Mostly the environment, the local environment of orbitals, moves from being rotationally invariant, like SO3, to being invariant under the symmetry group of the lattice. Moreover, and this is very important, when I add an orbital on one site, that orbital will now transform under representations of the site symmetry group of that site. And that's why we introduced site symmetry groups. So when I add orbitals in graphene on these positions, which is where actually graphene orbitals lie, the representations of the orbitals, or the wave functions of the orbitals, were transformed under the representations of the site symmetry group of this guy. So we'll transform under C3V. Okay? Now we can classify those representations. Okay? And the point about building the full group, the reason why I build the full group here out of site symmetry groups, so I build the site symmetry group of this guy, then I took operations to build the full C6 space group, is that we can then build the full band by just taking a representation, taking an orbital on site, and inducing, it's called a mathematical procedure called inducing. It's a very easy, 100 centuries old procedure, inducing a representation in the full space group. So we're going to think of bands in the next lecture. We're going to think of bands not as eigenstates of the Hamiltonian, but as representations. And an electron band is just a representation of the site symmetry group that was induced in the full space group. So I have all these orbitals at sites. They have some site symmetry group. They transform under some rotation, under some representation of the site symmetry group if they sit here under this site symmetry group, etc. Now we have to translate them all around the lattice. But all that does is taking one orbital in some representation and making another bigger representation that includes the translation group. So we're going to think of bands as abstract objects, which are called band representations. And those band representations, just like any representation, have universal properties. So that's what hopefully we're going to do next time. Thank you.
One question about this foundation. When you have p orbitals, for instance, you define this K, Ky, Pz, and for isolated atoms, it's equivalent because it's
Right.
environment. But then when you combine with the crystal, you have to say...
So I'm going to do exactly that. I'm going to classify exactly those representations. In the next lecture, I'm going to put orbitals here, classify all the px. So pz representation becomes this one-dimensional without spin. With spin is two-dimensional. Px, py is two-dimensional without spin. So I'm going to work that out in full detail.
In terms of chemistry, the chemists they talk about chemical bonds. So
That's right.
do we get this as an outcome of the procedure, or
So
we have to put it?
no. So in terms of how px. So if you want just crystal field splitting, which is just on site, basically, if I don't want to look at hybridization, I can then look at hybridization. But if I don't want to look at hybridization, if I just want crystal, the zeroth order, no hopping, I just basically know that this guy lives in an environment that's C3V symmetric. So I only need to characterize how, so Px, Py, Pz, Px, X, Y, Z are representations of SO3. This is a large group, and what you really have is just the group C3V, which is a subgroup of SO3. So all you need to do is called representation subduction, and you take this SO3 subgroup, this representation, and you subduce it to the symmetry group to the site symmetry group. And I'll show how to do that explicitly. But basically, it's a very simple procedure. So then when you hybridize, things get more complicated. So for example, if I have orbitals here and here, they can move their center of charge and move here, and they can become, the center of charge can sit here. And those depend on energetics of things, but the point is this theory will classify all those. So yeah, thank you.
Yeah, will this include like special cases where we have, for example, Sp2 hybrid orbital where symmetries do not apply?
So it will include, so Sp3 is not a representation of graphene.
Yeah, sure, but
So it'll include things that it basically tells you that you have to classify everything by representations of this symmetry group. So Sp2 is a representation of this guy. So Sp2 will be included here. So Sp2, if I just have px, py, and s orbitals, what I can form is I can form these bonds like this. Okay, and Sp2 hybridization means that these orbitals are hybridized. So it means really that the center of charge has moved from here to here. So really what it means is that the bands, any electronic band that will come from Sp2 hybridized orbitals, will actually have to be a representation induced from this site symmetry group. Because the site symmetry group where the bands have now come together. So if they hybridize, it's basically moving the center of charge here. It's a very important question. Moving the center of charge here. So you don't get induced from here anymore where the atoms were sitting. So the atoms are sitting here, but the center of charge is, Ivo and Titus mentioned, can move anywhere. So I can move the center of charge here. Has to be through a phase transition. I can move it here, and then the bands will get induced from this site symmetry group, and they'll have different properties, but the point is I can classify those properties. So it includes that.